Good morning, distinguished guests, speakers, and fellow participants. I am delighted to welcome you all to this session, Material Science and Nanotechnology. Today, we have honor of hearing from leading experts who will share their latest research and insights into how these fields are driving innovation and shaping the future. Now, I would like to invite Dr. Bharat Garu onto the dais, the session chair of this plenary session. I request P.G. Rao Garu to felicitate him. Please help P.G. Rao Garu with the Upavastram and plant. Thank you, sir. Dr. Kale Garu is Emeritus Professor and also scientist in CMET Pune. He is actively involved in nanostructure materials for various applications. He has demonstrated many technologies including battery and hydrogen. He has vast experience of 35 years and completed projects of more than 100 CR as a chief investigator. He was a Director General of CMET and heading all the centers of CMET. He has completed many projects, guided 22 PhD students, published more than 290 papers and filed 28 patents. He is in the list of 2% world scientists and ranked in material scientists. He is the Fellow of Academy and also life member of ICS and MRSI. There are many awards on his credit. Sir, I would like to hand it over to you from here.
It's a very important session. Material science and nanotechnologies. As everybody knows that materials are the backbone of all technologies. And today we have a very experienced scientist, like from the DRDO. 3-decade experience is not a joke because we have got a lot of practical experience. And we have 2 directors from DRDO, so we are lucky here in this session. And we have 2 very young scientists who are working on the nanoscience and nanotechnology. So we have good combination today. And as you know that materials are very important and we are scientists, we know only practical things. So we'd like to know how these science behind the Ayurveda, because Ayurveda it is not recognized worldwide because of some problems, like we are using that bhasma like Bharat, mercury or lead and all these things. So it is not recognized because we are not able to give them scientific proof. And that big project we are doing now, so with Shekhar Mande and ourselves, we are, Dr. Bhatkar is also there. So we are trying to find out the science behind the Ayurveda and even spirituality, what is really happening or something like that. So we are today, we have good scientists today and they are more practical oriented and definitely their experience will definitely help us to for this mission. So today we have 4 talks. First talk is from Dr. Namburi Prasad. He is the former director of DMSRDE, DRDO. It's a very well-known laboratory, and he has a great experience. He is a great honor. He has a great honor to introduce. I have a great honor to introduce Dr. Prasad. He has joined DRDO in 1985 after obtaining a BTech with honors from the prestigious Indian Institute of Technology, Banaras Hindu University, Varanasi, UP. Then obtained the PhD degree in metallurgical engineering. He has been serving the Ministry of Defense for more than 3 decades. So that is a very long experience in the defense. Then he was outstanding scientist of DRDO and director of the premier national functional materials laboratory, the DMSRDE or DRDO in Kanpur. It's a very well-known lab and he was the director of this lab. And then then retired in 2020. Recently he is retired in 2020 and he still continues his work. Dr. Prasad has vast experience and contributed immensely to the development of several defense systems such as LCA, MK1 and MK2, AMCA, Kaveri Aero Engine, Astra and Helena missiles, nanocomposites for naval propulsion and advanced personal protection systems for Indian soldiers. He has been consistently the chairman, president or member of 10 plus different national committees and bodies, including the ASM International Kanpur, then DRA Paris Hyderabad.
First of all, I would like to thank Shastri Garu, whom I know for quite many years. Not as a material scientist, not as a scientist, but as a true Indian. Shastri Garu comes very close from my native place, Elur. And I happened to meet him officially in the chambers of late Parekar sir, because I had given the recommendation for his project proposal in 2015 when it was submitted to DMSRDE. It was lying for quite a long time. And I took over that laboratory. I immediately gave the sanction because I always see worth whenever there is an Indian effort which exceeds 50%. Hardly any such kind of proposals come in the, the levels of director recommendations. And it was granted. I am happy that, today the SRIVT has become a national heritage center, especially material heritage center. During my talk, I will talk about what all the achievements we did in the last 40 years should be the golden era in Indian materials, if not the world at large. But let me also admit that the world at large got tremendously boosted by the discoveries that are made in the beginning of 19th century. There are, including the Raman spectroscopy and advanced electron microscopy and the latest analytical techniques which you can go up to atomic level of confirming nano level concentrational differences. DMR has got SIMS and etc. You can always see the advancement in the analytical techniques. Okay. With this brief introduction, again thanking the organizers and the chairman for a very nice introduction. I hope I will fulfill what I am supposed to do. I am happy that I made a statement that I spent more hours on this lecture because it's a quite difficult lecture for me to give. Normally I stitch around my standard subjects and then give the lecture, but this is a quite different subject. And I said, I spent more hours than the participants, but I'll take back my words. There are more participants. Let me put forth, when I talked Shastri Garu that I speak on this material evolution, he thought I was talking about, the evolution of matter. No. I'm talking about the materials which are important for the present day world. So the present day world uses around more than a lakh of engineering materials. And also 3 to 4 lakhs of total materials for which the base is all chemistry and chemical substances. If we understand this spectrum, it is very easy to develop systems because system requires one of the functional properties which are, I'll talk about them in the classification, very, very important. So I will talk about the past, which is supposed to go back even to a millennium. But I will more concentrate on present with the activities that I was associated in the last 30-35 years. Then I will definitely look into the future because future is always more important. If we live in the past and present, we will never able to see the tomorrow's present. Okay? So future I like to call it tomorrow's present. Role model, political visionary. For 2 reasons, Parekar sir is very jovial. Okay? He can handhold with anybody. Secondly, he is very, very strict about the values and also the time. The traits which are very, very uncommon in political leaders and leaders of his stage. And it's by fortune that I worked on 4 committees that he had headed. And he's also a metallurgist. Yesterday, Dr. Satish Reddy mentioned, we used to have meetings when Dr. Satish used to be on the right-hand side and Christopher sir on the left-hand side. Okay, so I don't know why I preferred that, but that's how it used to be, because Satish sir was an advisor and Christopher sir was an outsider compared to a minister. Advisor is always a first companion. So Satish sir always was on the right hand side. And he is the one who had also inducted me as a chairman of the Stealth Materials Subcommittee in the National Material Policy. And finally, when I said, sir, I'm going to write a few books, then he had really encouraged. In fact, he encouraged even Shastri Garu to a great extent. If we owe a single defense minister, maybe exception of Rajnath sir, who had banned several systems from import, I don't see any other defense minister. Maybe we don't know what Venkatraman sir had done. We heard stories about it, but definitely these two gentlemen stand apart. Next. I'll be very brief here afterwards. The slides will be very highly loaded. Please don't expect me to speak on all the aspects that I put it in the slide. There's one complaint that I always receive. Usually you don't speak on everything, whatever is there in the slide. You only passing make comments. That's the purpose of doing it. I would like to give a canvas to the people to think about what they can do, and rather than try to do in 20 minutes what all I know about the subject. So I'm going to do the past. Please go ahead. The past is the history and heritage. I'm not an expert on materials heritage, let me admit, and also my apologies. But next slide. You see this, the metallurgy past or materials past. Every second element, 40 elements are named after countries. 20 odd elements in the periodic table are named after the objects which we all love to call them even gods and heroes in the Greek mythology. And India especially, even today, leads in zinc metallurgy. Many people do not know that. The zinc is the one which has taken India to the world stage, and then zinc metallurgy is very, very important. Many people know that zinc is a highly electronegative compared to many metals. But in extreme conditions, zinc becomes a what you call anodic and then consumes itself to save the whole structure. So that's how the zinc metallurgy was mastered by Indians. And as this slide goes by, you will be able to see. And also, please repeat. This is the first place in Singhbhum, in Jharkhand, earlier Bihar. Suppose the first ever surface which has evolved on this earth, 3 billion years ago. Okay? So that research work. So I just took the snippet to say that why it is occurring, because physically thicker and chemically lighter. This is what is the materials about. We want to have a segregation of materials from one to other so that a liquid and solid get separated. That's how it is this small island it erupted, then it had become a whole earth. Next. This is my teacher of par excellence. I have not seen anybody come near to him, either in terms of academic degrees or in terms of his eloquence in speaking, the greatest orator. And you should look at his students. We have Ajay, my classmate, is ranked world number 7 in materials and metallurgy. And I figure out very next to him because of the year of we passed together, not for any other reason. Okay, you will see several great people in this, Professor Ramarao sir. And two people here, Professor Ranganathan sir and Professor Late Bala is my 1 year senior, for 2 reasons. Next. Before that, let me tell that Professor Anandarup, when he came back from UK, within 5 years, he started teaching Vedic metallurgy. And Professor N.P. Gandhi, who is a nephew of Mahatma Gandhi, when he was the principal at Banaras, he invited Anandarup sir from ISC to Banaras to lead the metallurgical engineering department. And he delivered LP Gandhi Memorial Lecture in 1973, and he talked about Indian metallurgy and its heritage. And if you see the IIM volume, you will see a masterpiece document on Indian metallurgical heritage. Later, he had also become like a yogi. He had instituted a separate center, just like our VIT, and then he printed Bhagavad Gita at the cost of 2 rupees from Bangalore in 1960, and then freely distributed 500 copies, whosoever came to his. That time 2 rupees was a large money. And then this is the last, one of the last copies which is given to me. So I reproduced it in the Anandarup Trust, and then it will be available online after some time. So this is the person, if I would like to say that metallurgy has a heritage in the heritage. It's a heritage of metals and materials that is a fundamental subject. Next one. This is his own disciple. Bala used to take Anantaraman sir's name like anything. He's a little crazy senior of mine. We also used to call him father. 1 year senior is always father. So Bala is a great person. I will over drinks only I can tell how he had done this book. How actually the Delhi pillar never get rusted. Nobody in the world could touch and then get the chemical composition of this pillar, but Bala did it in a very ingenious way. And he is a person who used to go to Himalayas and some remote place with his laptop and then sit down for 2-3 months and then come up with a book. This is one of that book. If you read this and the subsequent books, you will know why India is so great. Okay? There are several of that kind. Can we go to the next one? He himself had written this Indian iron through ages. Look at the finalities. After almost thousands of years, this structure remained. The final details of the nose and the tip of it and the lips, everything is fantastically retained, even in the most, abusive conditions. We never take pride in our heritage. 400, 500 years monuments in Europe, they get, a treatment like they will be having this kind of a display units where people have to pay through their nose to get to see them. But our own heritage, we take them as a stone and keep it as a souvenir in our house, which is a crime. Next one. So these are the 2 fantastic books. Sharada Srinivasan man had written 4 volumes on Indian heritage on gold, silver, zinc and mercury. And these are the ones which had made us proud that India had a heritage and knowledge, because metallurgy is nothing but art and science. It's not a mathematical sort of a thing. It's an extension of science. So if you take metallurgy as an extension of science, we said that how that science has become so valuable to the society, and there is an international publications by Indian author, Mishraji. The Indian metallurgy had written from US. Then we have a fantastic handbook, only through analytical techniques. I mentioned about it in my beginning of the talk, how analytical techniques have made materials unique. So these are the books I would like you to read, not that, the past I can read and tell in 20 minutes what was the past. Next one. So this is a special one where this seminar was conducted by Dwarka Das and brothers. There is a uniqueness of this family. The family of 5 brothers, all of them are either postgraduates or doctoral students or the faculty of Institute of Science. And they, from their personal money and the family money, they erected this, a national institute on Vedic sciences, Shri DRDO-DIA-COE. And I put a question in my open blog, why they selected Lord Lakshmi Narasimha, Garuda and Raghavendra Singh as the sequence. I leave it to you as a question, why that sequence? But these proceedings are also available in the ISC Bangalore library. And if you want to get up to 2018, what are the Indian heritage in metals and materials related to mathematics, science and technology, please go through those proceedings. Wonderful seminar, and it is conducted in a 1 day's time in a Tata auditorium. The fantastic proceedings. Next one. But I love this, I never seen any visionary better than Arunachala. He is the one to mount programs in DRDO, bring it from a test house to a system generating organization, made it almost the top. His favorite used to be this slide. I remember making this transparency for him in multicolor. When he came from US, he had brought this, and then, one of the visits he went in 1980s, brought this. In 86, he took this slide, and then he talked about how 12,000 years of materials development and evolution had taken place. And this is the one, but I find in this, every important engineering material is mentioned. And it is given as a relative importance. And the lacuna is, you add up any stage, it should become 100, it doesn't. Okay? So it is not mathematical. It's only a schematic or representative. But what we find in 1960s, the materials have taken almost one-third shape in terms of advanced metals, polymers and ceramics. That's when there is an optimum mix of material research happening. Thereafter, we have composites predominating and metals coming down. But mind it, again, the functional materials in the nano are ever evading compared to anything else. And this seminar should throw a lot of light and then show new directions so that in the next 20 years, the materials will be altogether different. Next one. And another slide is, this one he got Shanti Swarup Bhatnagar Award. This one he had received his Bharat Padma Vibhushan. And these are the Lifetime Achievement Award from Parekar sir in 2016. Next one. So I made it is the quantified numbers? No. Is it a importance, relative importance? How do we know? It's also not, it's only vaguely referred. So, but sir took a lot of interest in making this titanium and zirconium as an Indian heritage and Indian important material. And then in fact, he is the one to bring Indian coin of 5 rupees with titanium. Only to see that titanium gets into the usage in the quantities that will become the titanium production economically. Till that time, no titanium was produced at an international cost. To bring that, he got the coinage into titanium. So that's the visionary he has. In fact, he said, every utensil you use should be replaced from stainless steel to titanium. It doesn't have lush shell. Indian public will not use it. Okay? But it's a 10 times more corrosion resistant compared to stainless steels, which are more costly. It's okay. Next one. The another important thing is, this covers only 12,000 years. In humanity, if you remember, we said the first earth crust has surfaced 3 billion years back. So if you put it as a scale of 100 years, okay, of a Maga Yuga, because you people will understand much more than what I do, it covers only 3 months, what we know about material evolution. Rest everything is speculative. This itself also, Shastri Garu had collected more than 3 lakh documents. No other person had done that kind of an effort. Okay, so until otherwise there is a documentation and proof, now human brain will not work to accept any fact. The fact has to be a proof. So the proof has to be generated. So it's only we have in these 12,000 years also, I don't know how many people of you know, Jains are the first one to script anything on paper in 8th century. Till that time, this thing is only a hearsay. After that only we started getting our own scripts, and we had a few of documents from 16th and 17th centuries, and a few of them are retained in total. So that is the kind of Indian heritage value we have. Maybe it is even fractional, 6 sigma ka 1 it will go off. We have failure of 1 in 10 lakhs, that means the aircraft is not useful at all. Maybe our documentation also at that level. What knowledge we have is only 1 billion. So we can imagine how much the Indian heritage would have been and how much value it would have generated. Next one. So this is what motivated me to work, that Baldera said. He said publications are the life of a scientist. This is when I went to Similac. Oh, Similac is wonderful for documentation. You will have to do thousands of pages to get any small, even 1 kilogram material certified. Shastri Garu yesterday in his speech he mentioned, somebody asked him to get it certified. Thank God he did not do that. Otherwise he would have been repenting that he had gone to certification. As a certification director, regional director, I was telling you. But what Baldara sir said is, Ishwar, you have such a vast amount of data lying in Civil Act, please utilize that. I started writing these books actually on his instance, aeronautical books, which have become Guinness record. But in between, I was requested by the aluminum lithium book to be coming up from Elsevier, because I refused in 1994 to write an aluminum lithium book from Pergamon. But Elsevier approached me, I wrote in between this, and then this got published much earlier than this. But what is most important is, please go through this book if you want to look at the engineering applications and the basis for what we have to do to get into lightweighting. Right from zinc, magnesium alloys up to advanced composites are all covered in this 3 or 3rd volume. And Dan Miracle's article I would like you to see, the AFIR director who had given that, and the fantastic book. And then these two are the latest. Please don't buy them. Try to take copies from somebody. They are extremely costly. Each book is more than 20,000 rupees. So please don't waste your money if it is for personal purpose. But what is most important is, Baldev sir had also made me to realize that I should spend daily 2-3 hours on publications, whatever the activity you write. So that had made me, you can imagine, till I went to him, my citations, number of citations, hardly 1,000 or 1,200 like any other normal defense scientist. It went up to 4,000 plus, and then my I index had gone from 14 to 107 in 7 to 10 years. Okay. So 2015 I started extensively publishing, and that's where the index had happened. And if you all might remember, the big line in India said is defined by Dr. Professor CNR sir. Anybody want to call you a worthwhile scientist at international level, you should have a H index of his age, which is not at all possible for a defense scientist, let me tell you. We have 2 reasons. One is we cannot publish that extensively as academician. Secondly is, we should not also publish. If you give your ERIPR to the open world, the world is a cruel one. When it comes to money, it is the cruelest. We have to guard our rupee and to use it only for the Indian society. If everybody thinks about only publication, personal benefit, then the nation will be left with nothing but only pride, no prosperity. Next one. So coming to the present level, you all understand only from the defense in a small lab, how many products India has developed in the last 10 years. Dr. Satish Reddy talked about the emphasis Government of India has placed on indigenous production. Can we go to the next slide? These are the products that we have generated and given it to the Indian industry in terms of technology transfer, and all of them are done. In fact, I was mentioning to one of the organizers, the shaft technology of Jodhpur saved our Air Force from the immediate attack. Okay, it diverges our own fighter aircrafts, and then people will not know exactly that our aircraft is lying the moment you put a little bit of shaft and then bomb it. And nano is one of the wonderful things, and VIT can do that. And then several of these composites, 2nd and 3rd versions are required for the nation. To tell you frankly, the titanium half-alloys is a 20 years effort. We still do not have it in India at the diameters less than 8 millimeters. It goes through what is called impulse fatigue loading, and then the scatter in the life is too high for any aeronautical applications. So we don't have it, and half of the aircraft will be down if we don't have that product. Many of these products are so crucial, with one of the material or a product doesn't come up, we'll have to put the system down. One glaring example is the aero engine. So much discussion about it. Next one. These are some of the products that I proudly present it, because DMSRDE is supposed to be a sleeping giant or a dead elephant. So when I said we have already given this active army participation, there was people did not like me actually. You always talk too much. But when I said these are the documented, evidences, our chairman said, we should get so much revenue or royalty. See, that is the kind of thing. Many contributions go unnoticed because we do it as a routine from the government service. Because it's a servant. Job is for servants, not for making money. It is making the country proud with our own indigenous production. Next one. These are the systems, classical systems where we can make India export their defense products. And let me tell you, the Arjun experience is already documented as a DRDO monograph. If you read that, you will see the struggle of 45 years. You know, how we have gone through. And similarly, bulletproof jacket. I mean, I've been the architect of that, but the amount of criticism it has received before it became success, is a turnaround. There was a time, one of our own director generals threw the jacket, we successfully fired, threw it because it was not, the confirmed report did not come and he did not want to show it to Manmohanji. Okay? But in the very next exhibition, when Christopher sir came, the parliamentary committee wanted that as a first exhibit. In fact, the TBRL has put only a slide on that, you know, and this one. And suddenly our position was changed and then, you know, we had become the prominent display. And most important is the serpentine structure which is required for stealth application. Tell you in the world, nobody has done this experiment, the serpentine exhaust for aircraft. Next one. Chairman is already looking at the watch. These are the systems. India has already become a world leader and many more to come. Next one. So, these are the programs I am going to spend my next 5 years to talk about science behind these systems, how it has got done. This is my passion. This will be the volumes I will be looking forward to finalizing with my authors. And I tell you, each one is an effort of 40 to 50 years. And this is one of the best that this slide is one of the best that I can project to show cause the Indian achievements at the international level. If I were to put all the Indian scientists put together, there will be another 100, 150 material development programs. And all departments put together will be another 300, 400 materials. I might require the entire slide only to show that. You know. So this is the kind of effort India makes. But none of them realize because we are not able to generate enough money from that in the production. We are losing, as Dr. Satish Reddy said, manufacturing and manufacturing technologies. We are lacking not the technologies, we are lacking the equipment to make the products. India doesn't have any equipment or production facility making capability. We always import, then we have to import the entire production cycle. So we are ever dependent. Okay, next one. So the third part is the future. I will very quickly cover in 5 minutes. So these are mostly cited as not strategic. So there's an advantage for you, any one of you to take it up. Next one. The first is how it is being done theoretically. You don't have to go with the, what you call, the routine way of making, shaping, treating to get something. Okay? You can only do it from your mind. Okay? Indian Maharshis have done everything from their meditation. All Vedas which are supposed to come, even Lord Brahma lost the Vedic knowledge compared to Lord Vishnu and Shiva because his fifth head has gone. Okay? So he has borrowed the 4 Vedas only from Maya and then did the entire Srishti. Similarly, from an atomic level, from a subatomic particle modeling, you can go up to kilometers of structures, like aircraft carrier is a 1.5 kilometer or 750 to 1 kilometer long. So you can do all that thing with any material doing a computational material science. It's a leading program in DMR. Next one. Similarly, you can do computation materials, mechanics for several other applications. And then, let me tell you, aero engine will not come until we do what is a transitional stress strain analysis which goes from micro to macro deformation. Until you understand the very crucial dislocation mechanisms, we'll never get our blade. Next one. These are the ones which are India requires in billions of numbers, not millions. The flexi electronics, the electronics which will be there on our shirt, pant, or even on our mobile, everywhere the flexi electronics are required. These are the technologies and these are the applications only in the defense. If I have to write the other departments, again this slide will become very busy slide. Next one. And these are the production technologies, very few of them. But India doesn't have a single fab which can do this, single fab. And there are only news that XYZ collaborations are coming, but why not? India has so much black money or money underneath our cots. Why can't we take it out? Because we don't believe in our own genius. Whatever is the 150, 160 lakh GDP, India always in the circulation of 500 to 600 lakh crores. Why can't we invest in this kind of products and export them? We can do it, provided we have strength in our and faith in our engineers. Next slide. And these are some of the things which I have taken from the internet, and they are now today are present products that you and me buy. Either they are hidden inside the system or outside, they are all there. Okay? So these are quick requirement of flexi electronic devices. There is a center in Kanpur, flexi electronics. Anybody does it, that center is mandated by Government of India to help them. Next one. So these are some of the nanomaterials. All of you are interested in nanomaterials. If you can do any of these nanomaterials, these are all there in the books that I have published in the last volumes. If you can do this material by alternate methods, as Dr. Reddy had defined it as cheaper, alternate, but same capability or functionality, you will have a large market. Next one. This is a beautiful slide. One of the many awards in the metallography contest. They should look, something very beautiful. The flowers like this. These are all materials around micro or even nano size. You can see such a beautiful flower. It's a nature. Science is nothing but study of nature. So once you study the nature and able to explain and take it with a mathematical formulation or empirical formulation to a product, that is a technology. Once we have the technologies, many technologies put together for a purpose will give us a system. So this is the network that we have to do. Next one. These are the fantastic products that we have done, the sensors, and already these are competed. Indian itself, 10 prototypes have come when the ministry had put it for the open advertisement for procurement. So such is the competition. But look at the products that India is not making a headway. You only look at the imported items and then do the replacement. Good enough. Next one. And then next one. These are the ones that are torpedoes. Many people do not know many advanced explosives require special properties and special durations as well as lifetime. If you understand the chemical nature of a substance, how it gets degraded, you will be able to get the system very easily. And this is the one what is called the number of cycles. Look at the efficiency drop. If you can improve it the 10,000 to 90%, you have a world leader in this material. So that is the kind of improvement we require to get. So what is the capacitance given? 594 is the farads of gram, is the specification given by the Navy. And imagine that is if it is put it at 10,000 cycle in 2000 instead of 2500, we have no product worldwide to obtain. That is the importance of spec. Okay, next one. So these are, everybody talks about nowadays artificial intelligence and machine learning languages. Doesn't work for science. Human brain, which is HR, okay, human intelligence, far superior in correlating. If you look at the neural networks, what a brain can do, it's only 1,000 that advanced computer will do. What people are expecting is when the phonon and phonon technologies come up, the phonon data transfer rate, if you can filter the useful solutions from such computation, it might become little applicable for some of the jobs that we do daily. For example, if I pick up a coffee or a cup of coffee, what is the concentration of sugar I put? What is how much coffee powder I put? That can be a robo can do. And robo will become much more smoother to move instead of a stepwise. That kind of a thing only is possible. But several marketable solutions are coming. We are paying heavily for that. And all these are our Indians only. Our own brothers and sisters are doing elsewhere and then we are paying for them. I never take any, feel bad if I use some GPS system without paying it. Because my own brother or sister would have done it. But it is important that we do it in the country so that we will never get the blame. Next one. These are fighter aircrafts. F stands for fighter. The fighter aircrafts are US, F-15, F-16. Still one of the best. Rafales, MiGs. We are replacing only earlier versions. MiG-29 is one of the best in the world. Don't think that MiG is inferior compared to many. Sukhoi is the best medium weight craft. And LCA is one of the best by design. In the 10-10 category, there is no aircraft which can beat LCA. Even LCA 1, Mark 1. Only thing we require is India doesn't have enough money to weaponize it very quickly. And then we have to weaponize that one. I'll show you next slide.
Sir, we
Next
can
slide,
conclude
please.
now.
Yeah. This is the Astra missile that I gave the first the provisional clearance, and then this is the first trial which became successful. You know what is the trial? Only release this missile from this aircraft without this cockpit getting touched. Now there is a trajectory for the missile. If it reaches the trajectory, then this mission is successful. For which I have given a first my national award. Okay. So this is the kind of thing, we require. Indian government had ordered 5,000 missiles to be produced by the BDL, Hyderabad unit. Sometimes you go and see the missile, at least you can see. Okay. This is a fantastic achievement. Next one. So this is the one where Indian government wants to spend 1 lakh crores. AMCA. World over, they are doing, last 50 years, research. Then a stealth can be obtained by shape or by materials. But it's a mixture of two. One cannot do the job of the other. Okay, when we do that, we'll have the AMCA aircraft. When it gets matured, only with the material and shaping and using all the technologies I talked about, India can be maybe exporting the only fighter aircraft the world would like to have. Invisible aircraft. Next one. So this is the one I would like to leave it to the Vedic people. We have heard of Pushpak Viman. There is a popular saying, there is space for one more person all the time. Imagine the aerostat, which will be like this room big. But if you pump lithium into it, it will become this building big. Helium into it, it will become this building big. Imagine if you can pump hydrogen. Okay? But there is no material in the world which will have a pore size which will contain hydrogen to a cycle that the aerostat can go from here to even Madhapur center and come back. Hydrogen will get diffused there. Helium, neon is possible, but they also do not do the commercial application. So this is another, aerostat is a fantastic one, and it's powered by the ink, solar powered nano ink. That is what we, next. So, I will leave it with the fantastic video my friend had shared, and then you can, while the video is going on, you can read my concluding slides. Thank you.
Thank you, Prasad Garu. Very informative lectures and your vast experience and regarding materials to almost devices. So this is wonderful experience for our all students. So we can quickly have one or two.
Sir, you are telling titanium we can use it for our defense studies. But titanium it is costing 10 lakhs. Then how we can use it in defense and other?
See, the titanium is heavily price fluctuating.
Yes, sir.
Okay, so you have to talk to your users whether they want titanium to be replaced by 50 CVD steel. If it is not, please don't attempt it. Your user should agree to pay that much higher money.
Yes, sir.
Okay, there is no way when the price difference is 3 times, you can convince a user to fall down. Fall back for your
It is
system.
coming 10 times more.
Yes.
Then how we can utilize this titanium alloy?
Don't utilize it.
Then how we can improve that?
You improve it in the normal steel means better design.
So how we can decrease?
See,
the
we are
cost?
not an advanced country, or we have billions of dollars to invest for a normal system and then use the exotic materials. Mercedes car uses titanium. I worked on that. Or aluminum composites. India is not rich enough. See, the costing factor is very, very important. Next
One
one.
more thing, sir, is carbon fiber, sir. That is the most.
We don't have carbon fiber in
So
India
why
produced,
don't
we are
have-
importing.
Why we don't have that facility in India?
We don't have.
Why, sir? That's what.
It's very complicated. See, carbon can be produced at technology, but the grade of carbon that we get, okay, or the carbon from the pitch we get is not technologically suitable.
Electric also, sir.
Now I would like to ask our session chair, Dr. Bharat Kale Garu, to present memento, shawl and certificate to our speaker.
Thank you, sir, for your time and very
Thank you, sir.
One of the first life members of MRSR. My life membership number is M40, I still remember.
director of DIA-COE, IIT Jodhpur, and I am really thankful to organizer of Icon Bharat for giving me this opportunity to speak to you on this session talk on the topic Journey of Metals from Vedic Age to Modern Day. I am really grateful to Vedarshi ABS, who is the founder and director of SRIVT, and he is doing the commendable job, modern day technology, to bring out certain useful things and the ancient for the benefit of humankind for using the modern day technology. My topic, modern day, is a topic which bridges the ancient. We see the history of existence of human being on this planet Earth. We see that for millions of years, human being was another animal who is dwelling in the forest and barely surviving. But around 10,000 years back, when he started using copper and bronze, 3000 BC, he has started using iron. The metal has started playing as a very useful friend of human being, so that he can fight with the animals, with the enemies. He can using the metallic tools. So metal has played a very useful role in human civilization. In fact, we were the leader. If you see our ancient texts, Rig Veda and later Vedas, Ravindra, Nagarjuna, Bhagbhatta, very vivid descriptions of metals is there. In fact, in the mentions of 8 metals is there. If you see the copper metallurgy in ancient India, it has started with Harappan civilization, and we were aware about how to extract copper from the ore, zinc, and made brass. And we were aware about shaping of copper or bronze into different shapes by forging, sinking, raising, cold work, annealing, riveting, lapping, and joining. Harappan's objects discovered are spearheads, arrowheads, axes, chisels, sickles, blades, needles, hooks, and vessels such as jars, pots, and pans. Harappan also used gold and silver to produce a wide variety of ornaments such as pendants, bangles, beads, rings, or necklace parts. So in the classical age, copper bronze smiths supplied countless pieces of art like huge bronze statue of Buddha made between 500 and 700 CE in Sultanganj in Bihar using lost wax technique. We were out the gold, silver metal. Mainly it was used as an ornaments, jewelry, and in Karnataka, in Maski region, it is the oldest mine, the mid first millennium BC. And we were the master of iron metallurgy in ancient India. The Ganges civilization, which emerged, Vedic text mentions of a dark metal, while earliest texts such as the Rig Veda only spoke of ice, which it is now accepted referred to copper or bronze. In fact, the wood is from India, and we were master of making it, and it is basically iron containing a high proportion of carbon. And India was a major innovator wood steel, which was used to make the swords, and it was produced in South India from about 300 BC. And second advanced iron is the one used in the Delhi iron pillar, which consists of about 6 tons of wrought iron. And it is this technology that, in spite of around 1600 years of exposure to the weather, it has not rusted. We were also the innovator in zinc metallurgy, and we were the first to produce the zinc in the reverse distillation process. And in the Jawar region of Rajasthan, we have got these references. These are the dancing girls found in the Indus Valley civilization, made up of bronze, and these are significant. Casting technique has been used, which is currently also being used to produce the complex processes. So we were aware about this process. We can receive uh, hundreds of such type of artifacts, statues, which were produced by the ancient Indians, and casting techniques where the mold was prepared by the wax, and then it was by melting it, we were taking it out and then casting the metals and cooling and finishing it. These are the statues. We were also aware about the gilding process, that is how to coat these bronze statues or copper statues using the mercury amalgam applications. These are some of the monuments which have been recovered in the archaeological excavations, Jagannath temples, and the Damask sword made in the medieval India. These are the retorts found in the mines. These are around 3,000 years old, and they were used to produce zinc in ancient India. The mention in our texts are there about 8 metallic ores: Abrak, Vikrant Madi, Sonamaki, Vimla, Shilajit, Nila Thota, to take out metals, different metals. The processes used by the ancient Indians to prepare the iron pillars and other by instruments described in Rashtatnakar. Around 34 instruments are there, and there how to make these instruments and how to use them in various metallurgical processes. Now, for 3,000 years, the knowledge was first around 17th, 18th, and 19th century in Europe. A quantum revolution took place, and many metals were discovered like aluminum, titanium, uranium, tungsten, and I will cover them in my next slides. And the metallurgy, what was a tradition and art in ancient world, has been converted into science and technology. At that time, various industrial processes for bulk production has been developed, like blast furnaces and other furnaces, railways, household and agriculture equipment has been taking place. The most important discovery in medieval time was the discovery of aluminium, which is where the earth crust. In the ancient time, the knowledge of how to extract it, how to reduce it, was not there because it cannot be reduced. In the it was discovered by Danish scientist, and then in 1886 the Hall process has been developed to separate this metal from oxygen, and abundant in earth, and it's the light metal. And if you see the strength versus density ratio, the specific strength, it has very high strength, and these finds very wide application in aerospace, and as a foils, as a wire drying, as a corrosion resistance, and in other various other, and replacing many applications of iron and steel. The other important discovery was that of titanium. Again, this is very highly abundant in nature, and in strength wise, it is competing with the steels, and density wise, it is lighter than steels, and in many processes, it is again replacing, but it is slightly costlier today. And we hope that by that time, its cost will come down. This metal will find very large application in aerospace, as well as chemical reactors and things, and for storing hydrogen and oxygen. Titanium is used in rocket engines and other components. Titanium has a potential application in fields like medicine, marine engineering, and electronics, and shape is being remembered by the metal, and it will again take the shapes. So it can be used as a future construction material in the space where the normal processes cannot be used. The other materials are chromium, which is used and stainless steels are produced with this, and ferrochrome alloy is a key ingredient in stainless steel. Then there are other of chromium, especially in the high temperature materials, and then high corrosion resistance materials. Humankinds, and using the vanadium, we are producing various kinds of steel alloys, and it is being utilized for essential catalyst. And main use of this is as an alloying element, and head filled steel is one of the application where the this rail track are fabricated using these metals. It is highly damping in nature of vibrations, and it is very hard and tough, so it is being utilized in where the application where you require very high hardness, like jaw crusher, etc., etc. Application in reactors, nuclear reactors, as well as an alloying elements and superconductors. Cobalt is another element which has been discovered. This element is finding very high applications. It is being utilized in magnetic materials and various other applications. Nickel is another metal which is used mainly for coatings and platings, especially monal, nichrome, silver, steels, and nickel-based alloys in thermocouples, inconel, nickel titanium alloys, sap memory alloys. So this is highly useful. It has been again discovered in 1750 by Swedish chemist. Zirconium. These are the materials used in nuclear applications and medical, surgical instruments, dental implants, electronics, and many other modern day applications. Useful applications. It has been discovered in 1778, and applications are there to improve the strength, hardness, and wear resistance and air resistance of steel. These are used in photochromic glasses to control light transmission, catalyst in petroleum refining. Alloys containing molybdenum exhibit excellent acid resistance, so these are used as a reactor construction materials in chemical industries. Purview, because it is the lightest element, lightest metal on the earth, and some of its alloys are even lighter than the water. Very useful metal for batteries, and its application is increasing day by day, but it is not available in plenty. So how to get this element is a question mark. Probably the space mining can help us. And lithium has another application in the as a radioisotopes in nuclear reactors, lithium-6 fusion reactions, and also as a neutron detector. Another metal of importance for nuclear application is beryllium, rocketry, nuclear industry, electronics, and other refractory as a refractory material. Magnesium is another metal. It is the brother of aluminium, and magnesium is very useful. Many other metals are of importance. So, and its alloys with aluminium are being utilized in the aero applications as they are heated, and in the density ratio they are competitive. They are better than the steel components. Tungsten is another metal which is of importance to defense applications, and so finding out its ores and these things is a challenge, and future research is focused on these things. It is used in the cutting tools. Whites are the hardest material on the and used in the high speed cuttings, and various other applications, especially in the defense, like armors, nuclear fuel, and it is a metal which is highly controlled in this in the world, and this is used as a nuclear fuel as well as the radiation shielding and nuclear weapon. It is the strategic element which is controlled by different international treaties. Production of metals which has been used during the medieval times, and it has changed the ancient art of the blast furnace, open arc furnace, Bessemer converter, LD converter for steel making, electric furnace, electron beam furnace, rolling mills, hydraulic presses for forgings and extrusion. Coming to the modern day metallurgy science and tech engineering, which is the extension of medieval metallurgy. Various alloys I have discussed with you, which are finding various applications. Now in the modern day, in the missiles, submarines, nuclear, electronics, medicines, robotics, radars and automobiles. And we have also developed electron microscope and XRD studies. And the physical metallurgy has been started, where the phase diagrams and microstructure properties relations has been established. Now depending upon the applications, we can develop an alloy. In fact, we can design an alloy and we can simulate its properties, and then we can develop it. So current status, if we see the metals and alloys, there are the iron carbon alloy systems where the steels are there and carbon cast irons are there, then alloy steels are there. And other than the iron carbon steels, we have non-ferrous materials like aluminum, chromium, copper, magnesium, nickel, zinc and silicon. We have stainless steels, particularly are used where resistance to corrosion is important. Aluminum alloys and magnesium alloys are commonly used when a lightweight strong part is required, such as in. And for non-magnetic application, nickel-based copper alloys like Inconel are used in high-temperature applications, just such as gas turbine, turbocharges, pressure vessels, and heat exchangers for extremely high temperature. And single crystal alloys are used to minimize creep. In modern electronics, high purity single crystal silicon is essential for metal oxide silicon transistors and integrated circuits. Nanomaterials have, by reducing the size of the metal to a nano size, various innovative properties are developed and being developed for application in robotics and space construction. We also have converted metallurgy now into a material science and engineering, where various composites have also been developed which have replaced metals into various applications, especially the aerospace applications. And we are now using the computer and softwares for alloy designing and simulations. And we also working for, if you see the modern metalworking processes, casting, forging, rolling, extrusion, machining, sintering, fabrication by gas cuttings, and many more. So basically, and we are also have mastered the heat treatment processes, wherein by changing the microstructures, by giving its different thermomechanical treatments, we precipitation hardening, annealing, quenching, tampering, and in surface treatments, carbonizing and nitriding are very well established process. Improvement, thermal spraying using HVOF, plasma spray, flame spray, arc spray, and metallizing, electroplating and electroless deposition for surface treatments are there. So metallurgy has moved from a very raw application like a copper form available in the meteorite to a well-defined way, extracting metals from ores, making its alloy in various processes, and then giving it various treatments to have the desired properties. Now I will cover some part of my work which I have done for defense. These are the chaff materials. So when the engaged by a missile, it gets a signal, and to safeguard itself, it emits very fine metal fibers called the microwave dipoles, and millions and billions of these dipoles are ejected by the aircraft. That it has it becomes like a pseudo aircraft. In the radar, it is seen as it is giving more signal than the actual aircraft, so missile get diverted to it and it gets survived. Apps, and not only we have developed a very good materials which is better than the imported materials, but we have developed testing. It is found that it is very highly useful. These are the processes we have used. Innovative process by dissolving, we can reduce that 10 micron diameter to less than 25 micron diameter in a single pass, and multiple fibers passed. So by this technology, we have established a plant facility producing around 10 lakh meter per day, and this is successful technology where aluminum wire dia of 125 micron is passed through the chemical bath, and then a surface treatment process given to its color. And these are the property have been, you can see when these are tested in a microwave RCS monitoring facility, DLJ developed giving more than 30 to 40% more than the conventional chaff which is imported in nature. So this is what I want to cover, that metallurgy and metals have proved a very useful fertilization, and its use is going to be continued in different. And I thank the conference again for giving me a chance to speak to you, and thank you very much.
Dr. Goswami is from, he is assistant professor, Department of Chemistry, School of Applied Science, Humanities, Vignan Foundation for the Science, Technology and Research. Earned his BSc in Chemistry from Presidency College, Kolkata, and MSc from IIT Kanpur. He completed his PhD at Kale University and conducted postdoctoral research at Leicester University and Berkeley University. His current research focuses on synthesizing and characterizing nanomaterials for application in catalysis, energy, and environmental fields. Dr. Goswami has over 50 publications, 3 book chapters, and 1 co-edited book, aiming to address modern challenges through unstable nanomaterials. Please join me in welcoming Dr. Goswami, who is talented research and has a deep publication record.
I sincerely thank the organizer for making me a part of this. Normally, we don't get a chance to have a discussion and talk about this kind of technological aspects of it. I'm mostly an academic person who does a little bit of research. So for me, it is a kind of very intriguing to get to hear about so many technological advances that India has made over the years. As far as today's discussion is concerned, or today's my presentation is concerned, I will be, because of time constraint, I'll be only focusing some of the aspects that we do in the lab, particularly focusing on sustainability. But before I go to that particular part, let's focus on the major player here. So this is normally my group. Mostly, just for the students, these are all MSc students who have worked in our lab, and we are really fortunate to have them. They are now well placed either in industry or they'll be pursuing their PhDs also. But in addition to that, there are 4 major areas that we normally work. One is related to energy and environment, materials, mostly on the nano side, then catalysis and organics. So as far as organics part is concerned, today we will not discuss too much about this part, but mostly we'll try to restrict ourselves towards discussing about this. So Along with this, now there is a one part that keeps coming every time when we start discussing about science. So the part that we keep discussing is particularly sustainability. Now I know that the term sounds cliche because we have been hearing this since I was a child. So, but unfortunately, during my study, no one has told me. We heard the term, but no one has told me the ways to make a particular process or technology sustainable. And now we are old, or I'm not that, hopefully I'm not that old, but now the problem for us is actually, it is very, very challenging to get an idea and make it into a sustainable thing. So that's why I encourage all the youngsters who are here, so start thinking the sustainability term when you start developing your own ideas. Okay? Because eventually, at some time, we cannot keep on thinking somebody else will do it for us. Okay? It's not going to happen. It's better we all come and start taking a lead on this. So now, along with this part, another aspects of this so-called sustainability is waste to wealth. And most of my presentation I'm going to be talking about at least that point, utilizing certain waste material and how we can try at least our attempts to convert into something which is, so to say, a better version of the waste. Okay, but definitely it has some good purpose to be utilized for. What next? So before I joined Vignan, actually I have been privileged to have been working or have been involved with certain projects which lead to generate lot of good publications. But interestingly, knowingly or unknowingly, you see, if you look at all these, you see the particular metals or the figure that I showed, all of them except this one, all of them knowingly or unknowingly actually comes under this region. So that means that when we are doing, we knew about it, but we are not aware enough to make sure that we can continue with it. But anyway, this is one part of this. So most of the things are based on catalysis, which I will not discuss this today because that is what we have been doing. We will continue to do it. But when I join Vignan, then the next thing comes, what is next? What we can do, because obviously being in a private university, we have certain limitations in terms of availability of instruments and all these things. So what is next? What we can do? So we have to some way or the other start thinking in the context of what is available and how to make it work. So as simple as that. So we start asking questions, what's next? And in this case, we started asking questions, mainly 3 questions. If you can answer for your part, most likely, most of the things are going to be solved or taken care of. Solve is a very big word. We cannot solve the problem just like that. Okay, Sir, I was mentioning 45 years. And think about that, I am 45 years old. So since my birth, everything is put into just to make only one product out. So solving is, for youngsters I'm only talking, solving is a big term. So do you have a problem to tackle other than the catalysis which you are focusing on? So one thing that we found out that there is one problem that we can tackle, that is the treatment of dye-contaminated water. Why? Because even after discussing for more than 30 years, we are still not guaranteed a single material which is going to do the job for all. In fact, because this was not my field when I started working on it, the more I started working on it, I thought that should be the question that I should be asking, that should I make only one product which can solve this purpose? More I started working it, I realized that it is not going to be like that. You need to make your choices, which material to be used for what kind of dyes. Okay? So as far as this is concerned, this is a very schematic diagram of why you need this, is that you generate in industrial scale, you generate a lot of dyes, especially in textile industry, and they come into the downstream, and eventually what happens is that somewhere or the other you need to take care of this, and this is where our nanotechnology can help us tremendously. We have these options that are available to us. These are the materials that are also available to us. So you just have to mix and match, but except that you cannot take anything just out of this box and start mixing with this, because you need to know what these dyes are and how they will interact with the materials and in which mechanism. So apart from that, there are few challenges which exist in the areas of this so-called treatment of dye-contaminated water. The challenges are the efficiency, which I spoke about. Not a single material can solve all the problems. Regeneration and reusability. From academic standpoint, we started seeing lot of articles which says that this dye can do this. I mean, this material can perform outstandingly. But we now, except in last 5 years or so, before that, we hardly saw anywhere where they started mentioning these parts. That becomes a problem. Yes, we can publish 100 papers out of this, but irrespective, we can never get out a product out of this. Because if you can't make it sustainable, one of the sustainable conditions to make it reusable, that's not going to solve. So there are mechanistic insights. In fact, then we later found out that one of the reasons why we keep having these problems, that we have very minimal idea about how this mechanism works. Yes, from chemical engineering aspect, we have a lot of things to talk about. But unfortunately, we still don't know exactly how this is done. Okay, so we need to tackle this. There are synthetic challenges associated with the nanomaterial that we do. We cannot really synthesize a nanomaterial which can be very, very expensive and does very efficiently. Even if it can do very efficiently, that is not going to be a sustainable choice. Last but not the least, there's a validation study. Sir was mentioning about using computational power to validate your whatever technology or process or material that you have made for any kind of process. The earlier papers also lack that.
So the challenge is the cost effective one.
Cost effective, we'll come to that. Don't worry. We'll really discuss. So when I say efficiency, that actually takes care of this cost effective ones also.
Efficacy.
Efficacy also, I should have mentioned efficacy, correct? So now, the second question that I had asked is, do you have enough background to tackle such environment point? When at the beginning, we, along with the students, we decided to have a meeting. We said, do you have enough background? The answer is no. That time it was actually an answer which was no, because we didn't know how to do it. So what is the solution? Solution is, if you don't know something, just don't shut the door. Just go and explore. That's what we did, actually. So we started discussing and exploring further things. So as a snapshot, what we are going to do is we are now picked up a very few so-called combination of dye and adsorbent, and we'll make sure that we learn from them. They are not from waste materials, but they will give us enough information to take it forward so that we can develop something which is more cost effective. Okay. So the first two that we tried is, one is the halosite, one is the pyrophyllite. Interestingly, there are a lot of literatures on this, because they are clay materials. So huge amount of literature that are already there. Unfortunately, there are not that many literature on their absorption efficacy. In last 10 years only, this actually started exploring. There is a very specific reason for it. The reason was that people knew about their structure and everything, but only thing they did not know how to correlate with those structures with the adsorption part. So, and they are natural nanoclay. Again, we are not doing anything, so to say, extensively expensive in order to take it forward. So, in few slides, I'm going to just summarize some part about those things. So this is how halosite looks like. It's a clay material, it's a layered material, which is an aluminosilicate. And eventually, this is your dye. This is a cationic dye that we started. Somehow it's not very good. Anyway, we'll see. So these are all technical aspects. If you are really interested, I'll be happy today. Because of time possibly, I don't want to spend some time. The adsorption part, experiment, especially for youngsters, very simple. You take a dye solution, dump halosite to it, or your material to it, and you see whether it's absorbing or not. You can calculate how much it's absorbing based on a lot of the other data as well. You can come up with a theory or the mechanism related to it. But again, does this solve the problem that we actually discussed? So these are again some of this little bit characterization. These halocytes are nanotubes, just to show. 5 minutes, sir. So now in this case, we have also done some other things. IR, BET. Unfortunately, this is not a very, they are not porous, so that's a challenge we can relatively definitely improve on. So we are still working on it. These are certain batch adsorption study to show how the percentage of removal actually varies with respect to time, amount, dye concentration, and temperature. Oh, 5 minutes, the first one. Yeah, okay. This is the validation study that I was talking about. Okay. So in fact, we did validation. We showed that how instead of having this particular one, where you use one factor at a time process, we can actually make sure that how the interdependency of different factors lead to the optimum efficiency. So we can recycle it. That was something that was missing in the big previous literature. So, and we did some, so to say, kinetic and thermodynamic calculation to find out whether the process is exothermic, endothermic, whether it's spontaneous or not. Based on that, we came up with a mechanism to show that this process is governed by a lot of diffusion parameter. In addition to that, depending on which pH range you are working, we actually have different types of mechanism. The second one is a pyrophyllite nanoclay. It's pretty much, it's very simple to that. It's again a clay material, but one interesting part that we found out in this case and as well as the halocyte case, that on the contrary of a lot of other researchers who have said that there will be a so-called interlayer adsorption, we found out that explicitly it is dependent on the concentration of the dye that you are using. Because at a low concentration, what we found that most of the dye is going to be on the surface only. We have proven it by IR and all this thing, XRD. Once you keep on increasing the dye concentration, there's a possibility that it can go in. But there's also another possibility that there will be a multi-layer adsorption on the surface. Okay. So that makes this adsorption mechanism very, very challenging. Because depending on your pH, depending on reaction condition, depending on your concentration, all the mechanism will change. So what I wanted to say is that just having one particular data point at a certain concentration will not solve the general problem as such. Okay. We still have a long way to go. This is, for time being, is the same thing. How it works, what are the characterization. But eventually here also, we came up with another mechanism depending on both the surface charge on the pyrophyllite structure as well as the pK of the dye, and we said that it's predominantly dominated by so-called Coulombic interaction. We did recyclability as well as our regular RSM, response surface methodology, to find out the interdependency of different parameters. This is pretty much the mechanism. Now, when I say decontaminated, I sent this to a paper, they said, okay, you say decontaminated, but it's actually not decontaminated. And I appreciate that reviewer actually, because when I say decontaminated, it means it should be free from everything, right? This is not free. You have this additional bromide ion here. We are not removing the bromide, which we need to. These are the certain things which are completely ignored in the previous literature. We appreciate that. We have said, yes, we'll change that one. But I wanted to show that these are certain things that you need to make sure that you have some way or the other defend or tackle source problem. So what's next? So we have already solved this problem. Second one is, the third question that I said, the third question is, can you extend this for this acquired knowledge that you had for the idea to incorporate the notion of waste to wealth? Again, maybe, because we don't know. But then that time, we are very excited because now we know what to do with this, or know how to do with this. So what we have done there, we take this idea, and we move it to something, another different types of adsorbent for the same similar dye, but that is called nanocellulose, which is actually can be obtained from different waste materials. In this particular case, this is a waste-derived material. The waste that we have taken is nothing but a coconut coir. We have taken this is a standardized procedure. It is not very, we should also appreciate the amount of work that is done. This is a standardized procedure to remove all the lignin and other side products from this to finally get the nanocellulose. But when I did this, does it actually look like nanocellulose? That question came into picture. We know that we can solve this problem. In fact, it looks like this. See? So they are, in fact, tubular structure of nanocellulose. We can characterize them. We can do a lot of other kind of study. We did again batch adsorption study, and we found out that after regular thing, we can also do this recyclability part. So this is, think about this, slowly from your natural clay plant, we are moving to a nanocellulose part. Now nanocellulose, which is waste-derived, it is not only can absorb this, but at the same time you can actually make sure to recycle this multiple times. So that means our job is done, is it? That's the second, last question. So last question is this one. With this I'll stop. What's next? Because up to this is a story that I said, okay, we started with this is how we developed, and we followed. What is next? Can we start using one kind of waste to get one type of material, but with multiple applications? This is our next goal. How did we do that? Again, we have taken these parts, but we extended that to something else where we change eggshell. Now, you may find that there is no relation with halloysite, cellulose, and eggshell-derived materials. But there are, in terms of sustainability concept, there are certain relations. We have tried to move from so-called this natural nanoclay towards this waste-derived system. Now, you know eggshell, how abundant it is. It is not, and most of there are also literature on this. When we started doing this, we got excited, so we said, okay, we only focus on this part. But later we found that people have done eggshell based, especially because you know all the eggshells are calcium enriched. So they have used this as a supplement, calcium supplement. They have used this as a catalyst for a lot of reaction, especially for bioethanol production. Right? So we said we cannot then just outcompete those parts. So, but we can still start working on this. We can use this to utilize this as a nano vehicle for the drug intercoupler. So slowly, from this concept of the knowledge that we have from dye, we are now using the similar thing to develop a drug delivery system. Another one, we can also utilize that and use as a non-innocent support for CN coupling reaction. So how we do it? This is a very simple procedure. Not that anyone with a furnace which can go up to 1,000 can do it, because it does not need any fancy other things, no gas or anything. It's a muffled furnace thing. So you take eggshell, you just reflux it to get rid of all the organic impurity. Then you hit it at 800, you are going to get this calcine eggshell powder. If you use that with copper 1 or copper 2, you are going to get this one. Why copper 1 or copper 2 will be clear in a second.
What is the atomic number of helium?
Which one?
ET.
ET. This is ethyl. Ethyl alcohol. No. This is not a metal. It's just so now this is what we did. Now, what we actually did, we took the calcium eggshell. 2 minutes, I'll finish it. Calcium eggshell powder, very nice we have done. It's very simple to do. We used an intercoupler. It's a very important drug. Why? Because this is a drug that is used for it's used for Alzheimer and other stuff. It has very low bioavailability. It does not stay. Even if you take 100 grams, it does not stay in your body. It goes out only, I think, less than 30% bioavailability. Okay? So in this case, what we have done, we have said, okay, can we combine this with calcium eggshell, which is calcium enriched? So we are going to provide a particular drug with both the things where you have a calcium supplement as well as the original drug. Okay. So this is, at this stage, we have made calcium supplement, it is dual drug delivery, higher adsorption, sustained release, biocompatible support. So in fact, we did that. This part is not published yet, but we have done this adsorption part. We know that it works. Only part is the remaining part. Again, all these so-called simplified version of adsorption processes are already characterized and already proven. Only thing was, we still need to know, these are
The first
nowadays.
cycle efficiency is not comparable to the earlier, no? 95, 97%.
This one.
Yeah.
No, because the problem here is what happens. This is a pH range. This is not
Near 90.
no. This is pH, sir. Actually,
Achha, that's clear.
that because we cannot. That's the problem that actually sir pointed out. That's the problem. The problem is it is not the adsorption that we are looking into. It has to dissolve also in your body, right? Otherwise, there is no point having this.
So, whichever the pH, this data pertains to first cycle, right?
Only first cycle. Correct. That is correct. Only one cycle only we did because our job is to take it to the next level. But desorption, we are still working on it. It's a little bit challenging than this. What happens was, depending on the pH, or whether it's you are taking industrial pH or any other pH, your calcium starts dissolving. So the adsorption amount that you are thinking you are having is not actually going to be there. So you need to think about that. In addition to that, there is a problem in intercoupon structure. We struggle for more than 6 months on that. When you change pH, intercoupon changes its structure. Okay, because it got 2 OH units. It's a catechol based structure. Catechol based structure.
Goswami, just conclude please.
Yeah.
Just last slide.
Last slide, yes. That's the last slide only. So we have done that for the catalysis part also. We know that this is the one which is working. Again, not up to the mark. Normally, people are used to getting 90 above percentage. We are not going there, but I still think that it has a potential to be taken to the next level. With that, I think I have done those. This looks promising, not finally there yet. So we have done this. With that, I would again like to thank Sir, as well as
Thank you,
organizer, as well as all the participants.
Shri, Jodhpur. It is great honor to introduce Dr. Yojana Janu. She is scientist CE, who is posted at the Defense Laboratory, Jodhpur, one of the premier laboratories of the Defense Research and Development, DRDO. She has contributed significantly in the field of materials for defense application. Dr. Yojana has instrumental in advancing DIA's missions to achieve excellence and self-reliance in low observable technologies. Please join me in welcoming Dr. Yojana Janu, who is the talented scientist. He has a deep publication background. Thank you. Please, keep quiet.
Very good morning to all of you. Sir has told me everything about me. So the wisdom of the past is the light of the future. With these words, I would like to extend my heartfelt thanks to the organizer of this incredible conference. It's an opportunity for all of us to get into the very important dialogue that is bridging heritage, the ancient research in the advanced technologies. So it's a reminder for us that the technologies we have developed or we are developing, the cutting edge technologies, these are deeply rooted in the knowledge, experimentship and the craftsmanship of our ancientors. So today I'm going to talk about one of my work, that is synthesis of titanium aluminum intermetallic by MASHS. MASHS stands for Mechanical Activation Self-Propagation High Temperature Synthesis. Technique and study its microwave absorption property in ceramic matrix. So first thing it comes in our mind that what is synthesis? Synthesis is very simple process by making or creating new material by adding some substituents or elements or compound. This is the basic concept of science and technology. It allows us to create different kind of material based on their properties and all that, for stringent requirement and all that. So the term material synthesis might be sounds new, but it is as old as our our human civilization. So our ancienters are the first material scientists. They prepared different kind of material with the resources available to them. So I'm going to highlight some of the ancient techniques as early material synthesis. First one is metal smelting. This is the most transformative process in human history. Thousands years ago, our the ancient civilization discovered that when we heat the clay and stone, when we clay and stone, we get the important at high temperature. We can extract the important valuable material from that. So the copper is the first metal to be smelted. The second one is alloying. Actually, my font and everything has changed in this laptop. The second one is the alloying. Alloying is also very much important synthesis technique. The ancient civilization came to know that when they add the two materials together, they two metals together, they get the third metal that is much superior than in the properties of their constituents elements. So bronze was the first alloy was discovered with a mixture of copper and tin. The third one is pottery and ceramics. It is also as ancient as our civilization. They used the ancienters made useful tool using the clay itself only. Then glass making. Glass making is one of the historical achievement in ancient time. It's involved the melting sand with the other materials like soda and lime ash at high temperature. The molten glass could be then shaped and cooled into the solid form. This is very much stringent technique because a lot of parameters need to be controlled. So at that time people came to know that these things we need to take care, like the heating time or many things are there. So then here stone tool making. Stone tool were made by striking stone like flint and create sharp edges. So this one was also a very useful invention by the human beings. Then fire and pyrolysis. Ancient civilization used the controlled burning to transform the materials. So pyrolysis is the thermal decomposition of organic materials in the absence of oxygen. So in ancient time, people used to create charcoal by burning wood in different kind of these, as mentioned in the figure, this kind of bhattis, and we can say. So material synthesis have a very rich history. So the field of material synthesis revolving from the rudimentary technique to the sophisticated and advanced modern techniques. So these are some glimpses that in prehistoric era, discovery of natural material, then development of metallurgy and ceramics, then advancement in chemistry, refinement techniques, then in early modern periods, the birth of modern science. Then in 20th century, the polymers, semiconductors, composite, nanotechnology has come in the picture. And in 21st century, we are doing the advanced multifunctional smart material with strategic applications, and parallelly we are also doing the application of modern technique for material synthesis following ancient roots, and as we are listening from since tomorrow in this conference. So we are working on that novel kind of material for strategic applications. So here I am talking about intermetallics. So intermetallics are very much similar to the alloys. So the only difference is the bond is that between intermetallics are partially ionic. And one of the important properties that is distinguished intermetallic from alloy, that its crystal structure is completely different from its constituents elements. So there are two types of intermetallics, that is stoichiometric and non-stoichiometric. Stoichiometric intermetallic have fixed composition, and non-stoichiometallic have range of the compositions, means the composition was not fixed, we can vary their composition. This leads to very important properties to the intermetallics to the stoichiometric intermetallics. So we are talking about titanium based intermetallics. So titanium based intermetallics offers many advantages, as they can be used in aircraft because of high strength to weight ratio, high corrosion resistance, low specific gravity, non-magnetic properties. Of course they are offering with high specific strength, and they are biocompatible material, and they are having good fabrication ability. So titanium based intermetallic can be used in many kind of application, including aerospace, medical, industries, and other special applications such as marine, sports equipment, and ultrasonic welding. Now we will talk about our material, that is titanium aluminite. It is also a class of non-stoichiometric intermetallic. So this is having the properties that is lightweight and high strength. Two phases of titanium aluminum intermetallics are received attention: alpha phase and gamma phase. And this is also this material can be used at high temperature application also. So this is the beauty of this material. It can be used in many applications like aircraft, space vehicle, industry, gas turbine, combustion engine exhaust and electric train, structural component, and high temperature furnace. So there are many synthesis methods have been reported in the literature for the synthesis of this titanium intermetallic, that is forging, metal induction molding, additive manufacturing, vacuum casting, spark plasma sintering. Every method has their unique advantage, but they are come with some limitations also. That is, these are the high energy consumption, time consuming, high equipment cost, non-uniform heating, and complexity in controlling the parameters, because it is very difficult to get the pure phase of that kind of intermetallics, because sometimes we get the mixture of that, so that material will not be useful for the required applications. So we have adopted a unique technique for the synthesis of titanium aluminum intermetallics, that is MASHS, as I told earlier, that is mechanical activation, self-propagation, high temperature. It is a combination of two techniques. One is mechanical activation and second is self-propagation, high temperature. So the beauty of this technique is it's a unique effective method for preparation of advanced material, and the enhance overall reactivity of the material. Then we will get pure material in very much less reaction time, and it's energy efficient also, and it has less environmental impact, and we get good yield also this product. So the procedure involves the selection of suitable material, then mechanically activated that material, and then compaction of that material in reaction vessel, and ignite or heat the material up to that temperature for self-ignition. Then we will get our final product, and we process the ingot and collect the powder. So this is the method that first we will precursor, we use titanium powder, aluminum powder with AR grade, and then mechanical activation will be done in planetary ball mill with the optimized rotation period and rotation speed. Then we transfer this reaction mixture into cylindrical vessel and put the vessel in the shaft furnace, and then ignite this powder. Then we will get this kind of ingot. This kind of ingot we will get. Then we process this ingot and sieve with the desired particle size range, and we will get our final powder. Then we will characterize it by the various characterization techniques like XRD. So the XRD spectra reveals that there is no it confirms the formation of titanium aluminum phase as a major phase, and no residual phases are present there. Then also morphological study confirmed the irregular shape of the powder, and EDEX microgram confirmed the presence of titanium aluminum. Then elemental analysis and particle size distribution analysis have also been carried out. Then when we are using this powder for different kind of defense applications, we need to develop some kind of composite material by using this material. So we made a ceramic composite by using the synthesized titanium aluminide in alumina matrix. So this is also a very long process. First mixing and milling and drying and granulation to make the powder compatible for our applications. So I will conclude that we have established a unique synthesis technique for synthesis of titanium aluminide, and the developed process has capability to scaling up also. We can synthesize 2 or 3 kgs powder in one batch of reaction. Then the coating composites have been formulated by dispersing the powder in different concentration of that powder in ceramic matrix, and application and testing on strategic platform successfully carried out. So this is open for that. Can we explore the synthesis of strategic or advanced or multifunctional material by the Vedic route also? Thank you so much.
I should thank to Dr. Prasad because very good information about the DRDO materials, their manufacturing, and how they struggle to have the device and all these things. And I should also thank to Dr. Goswami. Waste to wealth is also very important today because we are producing so much waste, and it has to be recycled, and so he has given the good information about the dye degradation and how to decontaminate the water. And I should also thank to Madam that intermetallic synthesis is very, very important because these materials are very unique materials, will be useful in so many places, including from energy to even high temperature materials. So I conclude this session, and I thanks to all speakers for their time and good lecture. Thank you very much.